Hey everyone, it's Bradley Bush with another algebra video for you. Today we're talking about partial fractions. So let's talk about our to-do list. First thing we have is a bird's eye view. So I want you to see the big picture. Sometimes you get bogged down, you can't see the forest, you just see the tree. So I hope to show you the forest. I hope to show you the big picture, so you can kind of feel, you can understand what's going on, and that, I feel, gives you power. The second thing we will do is we'll do a worked example. This one specifically talks about repeated linear factors. So I have a few different videos on partial fractions in my algebra playlist. If you need one that does not discuss repeated linear factors, please check out my playlist. This one will only discuss repeated linear factors. Let's start. Do you guys remember adding fractions? I know you're thinking, no, I can't get away from those things. I know, fractions are back. So say you've got 1/2 and you want to add that to 3/5. You can't because you don't have a common denominator. So 2 and 5, there's nothing common between those two numbers. So you think, well, let's multiply them together. And you get 2 times 5 equals 10. So you're like, okay, 10's my common denominator. So on the left fraction, the 1/2, you multiply by 5 over 5. And the right fraction, the 3/5, you multiply by 2 over 2. And that gives you 5/10 for the 1/2. And for the 3/5, that gives you 6 over 10. Now you've got a common denominator. So they're both in terms of tens. You can just add the tops. So you have 5 plus 6 in the top, and then over the 10 in the bottom. And then you add those together and you get 11 over 10. Great refresher. Now let's talk about a different kind of fraction. These are fractions kind of on steroids. So rational functions. Rational functions or rational expressions, if you're adding rational to rational expressions, or subtracting, you have to follow the same rules that you followed when you were dealing with fractions, because rational expressions are just functions. No, well, maybe, but that's really not what I meant to say. Rational expressions are just fractions, and they have polynomials in the top and or bottom of the fraction instead of just having constants. So they follow all the same rules that fractions do. So if we look at the denominators here, we think, well, we need to get a common denominator. And on the left, we have x minus 4. On the right, we have x plus 2. There isn't anything that's common about those two. Our unique factors here are x minus 4, x plus 2. So we do the same thing we did in the example above with the fractions, and we multiply these two things together. So that gives us our common denominator, which is x minus 4 times x plus 2. So now we start the business of getting both of the fractions to have the same common denominator. So on the left fraction, the 3 over x minus 4, it's missing the x plus 2. So if we add it, meaning we multiply top and bottom by x plus 2, the right fraction is missing the x minus 4. So we multiply top and bottom by x minus 4. Then we have to distribute our 3 into the x, which gives us 3x. We distribute the 3 into the 2. That gives us our 6. And then we distribute the negative 2 into the x, and that gives us negative 2x. Negative 2 into the 4, and that gives us positive 8. Then we just combine like terms. We have 3x minus 2x, which gives us positive x, and we have 6 and 8, which give us 14. So they're all over our common denominator, and voila, we have our new fraction. What exactly are partial fractions? It's a really good question. Let's find out. Here's the punchline. When you add two rational expressions, say 3 over x minus 4 and negative 2 over x plus 2, or subtract them, which you do in this case, you combine the two and you end up with some single fraction or rational expression. So you take two of them, you combine them, and you make another one. So when you're adding or subtracting rational expressions, what you're doing is it's kind of like you're getting in your car and you're going from the left side of the equation here to the right side. Like you're going to the store. Home, store. Home's the left side, the store is the right side. So you're going from the left to the right when you're adding or subtracting rational expressions. What if you wanted to go backwards? What if you got to the store, you finished your shopping, you're like, okay, let's go home. Well, that is called partial fraction decomposition, meaning if you are now at the right side and you're like, hey, I want to go back. So in other words, the thing that I started with was this single fraction. And I think, what if I want to go back to a bunch of smaller fractions added or subtracted together? Well, you can. That process of going back is what we call partial fraction decomposition. So, or partial fractions for short. So it's really not hard. All you're doing with partial fraction decomposition or partial fractions is you're taking a big complex fraction and splitting it up into the sum or difference of a bunch of smaller ones. That's it. End of story. Now you know the meaning of life and partial fractions. I should probably tell you that there are 5 types. Well, I guess really 4, because the 5th one is just a combination of the 4. There are 4 types of partial fraction problems. You have distinct linear factors. You have repeated linear factors, which is what we will discuss here. This is what we're doing in this video. You have non-repeated prime quadratic factors, and you have prime repeated quadratic factors. So you can have all 4 of those situations show up, and they could be combined together, one or more of those 4, which is the 5th category. So now you've had your review. Let's actually do a problem that has repeated linear factors. So all of my guidelines for you, all my steps are on the right in red. So those are helpful. You can follow those for any problem with repeated linear factors. So if they're helpful, maybe write them down and you can use them as a guide as you're going along later. So step 1, we need to find all of the unique factors in the denominator. Well, we can do this by looking at what we have. What do we have? Here's our first unique factor, x plus 2. And we have a second unique factor. Whoops. I wrote what I was thinking, x minus 3. This is the second unique factor. So we have 2 different factors there. Sweet, we're done with step 1. Step 2, are these factors linear or are they quadratic? How do we know? Well, we look at the exponents. So the exponents on the variables, that's what we look for. We don't care about this 2 out front yet. If we're looking for whether something's linear or quadratic as far as the factors go, we just look at the exponents on the variables. So both of these exponents on the x are just 1. So that tells us that we have linear factors here. If we would have quadratic factors, we would have seen a 2 above the x, but we don't. In fact, we don't even see the 1. And the reason we know the 1 is there is because we know there's a 1 there that's implied. So we have linear factors. So good, we're in the right category. We can follow these steps and we're good to go. Well, the next step, step 3, is to set up the problem. So this is how it works. For each of the distinct linear factors, we need to have a fraction. So we have 2 distinct linear factors, right? X plus 2 and x minus 3. So we need to have a fraction for both of them. And we're just going to put pluses between all of them, and we'll figure out if they should have negatives later. So we have x plus 2, x minus 3. They're going to have numbers in the top, right? We don't know what the numbers are, but that's the whole point of the process, is to figure out what they are. So until we figure out what they are, we're going to put in just placeholders. And instead of using x's and y's, because we already have x's in the thing, we're going to use a's, b's, and so on. So we have an a and a b. So if we did not have repeated linear factors, how do we know that they're repeated? Well, that's where the 2 finally comes in. We know that we have more than one of them, right? X minus 3 quantity squared. That means I've got x minus 3 and then another x minus 3. So I've got 2 of them. So I've repeated linear factors. So since I have 2 of them, I put x minus 3 once with the 1 power. And then I have to do another x minus 3, but with the 2 as the exponent. So if this original 2 had really been a 3, I would have had an x minus 3 to the 1 power, x minus 3 to the 2 power, and then x minus 3 to the 3rd power. So we also need to have a placeholder above the x minus 3 squared term. So let's put a c, because I'm just following the alphabet. You can really put whatever you want there. So step number 3 is done. We've set up the problem. Step number 4 is we need to combine the terms on the right. So this is where we use our skills from fraction world. We've got to get a common denominator, right? That doesn't sound like a lot of fun, does it? Nope, it doesn't. But lucky for us, we know what our LCD is. Our common denominator is going to be what we started out with, right? Up here at the top, LCD is x plus 2 times x minus 3 quantity squared. So we're going to look at each of these and see what is it missing and plop it in, just like we did with our fractions above when we changed the 1/2 and the 3/5 to something with 10 in the bottom. We had to multiply top and bottom by something to get the common denominator. So that's all we're going to do here. So the first term, the a over x plus 2, it's got the x plus 2, but it's missing the 2x minus 3's. So let's get those there. So we have x minus 3, x minus 3 squared. So we've got to multiply on the top by x minus 3 squared. What is the b term missing? Well, it has one x minus 3, so it needs a second one. So we'll put a squared there, and then up top, x minus 3 already. And what else? We need the x plus 2. So we'll multiply by x plus 2. So we have an x minus 3 times x minus 2. How about the c term? It has the x minus 3 quantity squared already. It's just missing the x plus 2. So let's put that in. X plus 2. So now we have a common denominator. All three of these terms have as their denominator x plus 2 quantity times quantity x minus 3 squared. And now we can rewrite this as one fraction. So we combined all of our terms on the right, and now we can take, let's see, let's do red. We can take all of the stuff in the numerator, put it down below, and put it over a single fraction, which is the common denominator. So we do that. All right. We need to move on to step 5. Step 5 says to rewrite the numerator on the right to look like the numerator on the left, and then compare coefficients. This is kind of a trick that we use, because you see, now we're looking at this line right here. Now we have some fraction here equals some fraction here. If these two fractions really are the same, then the bottoms have to be the same, which is already true, and their tops have to be the same. So the left numerator has to be the same as the right numerator. We don't know that that's true, but we hope it's true, and our algebra will choose these A, B's, and C's so that it is true. That's the whole magic behind this. We'll end up solving for the A, B, and C that make it true, which is kind of cool. So we need to do some algebra. So we'll take this numerator right here, and we need to just rearrange it so that we get all of the x squared terms together, all of the, like we have here, all the x terms together, and then all of the constant terms together. So as we do that, x minus 3 squared, I have already showed you here what that is. X squared minus 6x plus 9. And then x minus 3 times x plus 2. I have that written down here too. So we'll just go ahead and put those in. We have them here and here. Now I've got to distribute the a through. So I take the a, distribute it to the x squared. That gives me ax squared. 8 times negative 6x gives me negative 6ax. And a times 9 gives me 9a. The b goes through to the x squared, which gives me bx squared. The b goes through, to the negative x, which gives me negative bx. The b goes through to the negative 6, which gives me negative 6b. Then the c has to go through as well. So c times x gives me cx. C times 2 gives me 2c. So now I have all of my new terms. We need to get all of these squared terms together. So where are the squared terms? We have an ax squared there. We've got a bx squared here. We put those together down below. Ax squared plus bx squared. Now let's look at the x terms. So where are the terms that have x in them? Well, we've got a negative 6ax, got a negative bx, and we've got a cx. I think that's it. Those we put down below as well. We put those together. And everything else doesn't have an x. So we have 9a, we have negative 6b, and we have 2c. Those all go down below as well. So all I did is just rearrange. Everything else is identical on both sides of the equation. The reason that we want to do that is because you notice that in the pink, you can take these two x squared terms, and you can pull them out, right? You can factor out an x squared. So that's what I do. I factor out the x squared. And what's left? Just the a and the b, which you see here. So I do the same thing with the x terms. I have a negative 6a. That's right here. I have a negative b, which is here, and a positive c, which is here. I factored out the x. Factored out the x. And the terms without any x's, I just carry them down. So it's exactly the same as what you have here. So the reason that we like this, the reason this is cool, and I'm going to clean this up a little bit now so that you can see something. The reason we like this is, check this out. This is actually a really cool trick. So if this equation is true, meaning this equal sign right here is actually valid, that means the stuff on the left has to be exactly like the stuff on the right. Is it? Well, we don't know. What is in front of the x squared on the left? We have a 6. What's in front of the x squared on the right? A plus b. So if this equation is to hold, then a plus b has to be equal to 6. So that gives us our first equation. A plus b. I'm going to write it down here for equation 1. A plus b must equal 6. What's in front of the x on the left? Negative 14. What's in front of the x on the right? Negative 6a minus b plus c. So negative 6 minus b plus c must equal negative 14. Or both sides of the equation aren't the same, right? This is kind of a really cool trick. And finally, we have one more. All the stuff without an x. All of that. On the left, we see that all the rest of the stuff without an x is negative 27. And all the stuff on the right is 9a minus 6b plus 2c. So we know 9a minus 6b plus 2c has to equal negative 27. And now we have a system of equations. We've got 3 equations, 3 unknowns, and we have done step 6. We've built our system. And step 7 is to solve that system. So now we go back to a completely different topic, which is systems of equations. I have some videos on those if you are kind of shaky on that in my algebra playlist. We just solve the system. Once we solve the system, we have an a, b, and a c, and that gives us the coefficients on all of the different fractions that we are breaking our big fraction up into. So this is awesome. Let's keep going. If we want to solve this system, we need to solve for a, b, and c. I generally like to use the path of least resistance. So I can see already in equation 1 here that it's missing a c. It just has a and b. That's actually a pretty simple equation, right? So let's keep equation 1. Let's use equation 2 and equation 3 and get rid of the c term. And then we'll have another equation with a and b, and we can use equation 1 with that new equation and solve for a and b, and then come back in and find c. So we'll get rid of the c term from equation 3 and equation 2. And we'll do that by multiplying negative 2 by equation 2 and adding it to equation 3. So my equation identifiers have circles around them, just so I don't get confused between the numbers that I use for the identifiers of the equations and the actual numbers themselves. So here we have equation 2, and I'm multiplying it by -2. And then I just copied equation 3 straight from where it was. Nothing changed there. So what do we have then? Because we need to, we're going to have some stuff here. We have -2 times -6a. And that gives us 12a. We have -2 times -b, which gives us positive 2b. And we have -2 times c, which gives us -2c. And then -2 times -14, which is positive 28. Now, when we add those two together, what do we get? We get 9 and 12 give us 21a. 2b and -6b give us -4b. The c's cancel, which is perfect. That's what we want, right? And what are we left with on the right-hand side of the equation? 28 minus 27 is just 1. So we have a new equation. We have the equation 21a minus 4b equals 1. We'll call that equation 4. That's our new equation that we're going to use with equation number 1 to find a and b. Oh, I've written the equations, original equations on the right there just for reference. So now we're going to take equation 1, which is here, and equation 4, which is our new one we just created, and we're going to solve this new system with a and b in it. So I have that here written down for us already. This is a long process, so I've tried to have as much already written as I can. So if we're going to solve this system, what should we do? Well, if we take equation 1, a plus b equals 6, and we solve for a, that means we'll have a -b on both sides, and that gives us a equals 6 minus b. We can take that and substitute it back into equation 4 for a right there. So that's what we're going to do. We substitute a equals 6 minus b, which we got from equation 1, into equation 4. So here we have equation 4. We can see that we would have had an a here, but instead of having an a there, we're going to plug in what a equals, and that is 6 minus b. Now we have just b's, and we can solve for b. So we're actually getting somewhere, right? We're making some great progress. We need to distribute that 21, and what does that give us? 126. Oh, I don't want yellow. 126 minus 21b minus 4b equals 1. The 21b and the 4b give us 25b. 126 minus 25b equals 1. We're solving for b, so let's take the 126 to the other side. So we subtract 126 on both sides of the equation, and what do we get? Negative 25, b equals negative 125. Now we divide both sides by negative 25. And what does that give us? That gives us b equals 125 over negative 125 over negative 25, which is just 5. Hey, we have done something, right? We just found b. Great. So we can take that now and we can plug it into equation 1 because we have and we know that a equals, from equation 1, it's not a very good a, is it? We know that a equals 6 minus b. So we know what b equals. B actually equals 5. So we can solve for a now fairly easily, right? So a equals 6 minus 5, which is 1. This is awesome. We now have a and we have b. So we can take a, which we know, a equals 1, and b equals 5, and we can plug that back in to one of our original two equations, equation 2 or equation 3, because equation 2 and equation 3 both had c's in them. So let's choose equation number 2. Negative 6a minus b plus c equals negative 14. So instead of a, we have 1. Instead of b, we have 5. Now we just do some algebra. So we have negative 6 minus 5 plus c equals negative 14. Negative 11, negative 6, negative 5 is negative 11, plus c equals negative 14. Add 11 to both sides. It's kind of hard to see if that's a add 11, right? Not sure that's much better, but here we go. That gives us c equals negative 14 plus 11, which is negative 3. So we have our a, our b, and our c. Awesome. Step 8, we need to state our answer. So we proposed that at the beginning, this big long thing on the left here could be split up into 3 different smaller, simpler fractions added together. And we solve for the a, b, and the c. So our job now is just to put that in. Put the a, b, and the c in. Plug them in. So a equals 1, b equals 5, and c equals negative 3. So we'll have 1 here. We will have 5 in the middle, and we'll have negative 3 here. Just a note here. The negative, you see with the 3, that could stay right there, and you could keep the plus out front. But you could also have a plus 3 here and have a negative out front. Either way is okay. You can choose. It's just a personal preference, honestly. But we have our answer. Isn't that amazing? I think that's actually pretty cool. So you've seen a complete example of repeated linear factors. So how could they change this up on you? Say you're doing your homework, and how could they change this? Well, you have the other 3 categories that we talked about above. You could have just distinct linear factors, which actually is an easier case. 2 linear factors and no repeats. That gives you a simpler problem. A more complex problem would be repeated prime quadratic factors. So you have your linear factor here, and you have a quadratic that you can't factor. And you know it's quadratic because you see a 2 on the x, an exponent of 2 on the x. The way you set that up is above the quadratic term, you would put bx plus c instead of just b. But everything else, solution process follows the same as with the one we just did. The last thing they can do to throw things new and crazy at you is you could have repeated quadratic. So not just a prime quadratic, but perhaps you have 3 of them. So you would set it up just the way we've set it up before. You put 1 for each distinct factor. So we have x minus 2 and then x squared plus 2x plus 4. So you have the x minus 2 term with an a because it's linear. We have, notice we've got 3 of these quadratics. So we've got to do 1 for each of the exponents, 1, 2, and 3. So here we have the x squared plus 2x plus 1 to the first power. If you want, I can write 1 there. Then we have it to the second power and to the third power. And above all of those, we have some constant times x plus a constant. And I just use the alphabet. So bx plus c is the first one, second one dx plus e, and the third one be fx plus g. And then you'd follow the same process that we'd followed for all the rest of ours, and you'd be done. Hopefully you don't get one that is that complicated, because that would be kind of painful. But at least you know how to do it. So that's it. That's the video. Hope you enjoyed it. Hope it was helpful, and let me know if you have any questions.